Hi, my name is Bill Harrison. I'm a principal scientist at 26 Technologies, and I'm here to report on some research that I've done with my colleagues Chris Hathorn and Jerry Allwine on semantic foundations for high-level synthesis. So in today's talk, I'm going to introduce something I call the device calculus, which we've actually used in some previous publications as well. And what the device calculus really is it's a lambda calculus for constructing Mealy machines. And we have a denotational semantics for it formalized in AGDA. And we're going to show how this is used as a semantic basis for expanding the trust zone of high-level synthesis. To illustrate the device calculus, we're going to present a semantic specification of what we call idealized FERTL, where FERTL is a small open source target language for the Chisel hardware construction language. Idealized FERTL specifies a substantial subset of FERTL, although it's not the be-all gold standard for FERTL semantics. Our motivation here is as a foundation for high-level synthesis compiler verification, and in particular, our high-level synthesis tool, which is known as Rewire. And we also want a semantic basis for what in the reconfigurable community they call third-party IP modules. These are really libraries of functionality that get imported into hardware designs. So I'm going to spend a lot of time talking about the background and motivation for this work, because I assume that my audience is not perhaps as familiar with high-level synthesis as with, say, software science. So what is high-level synthesis? Well, the typical languages that you use to design hardware devices are what are called hardware definition languages, or HDLs. So you've heard of VHDL and Verilog. Those are examples of hardware definition languages. It's fairly well recognized among a large segment of the, let's say, computer architecture community that VHDL and Verilog lack what you might call software engineering virtues. Those are things that we might associate with a highly expressive software language, say like Haskell. So some of these virtues might include abstraction or modularity or program comprehensibility. And it's generally recognized, or frequently recognized, that these commodity HDLs lack these virtues. And so this motivates the research on high-level synthesis, or HLS. So the idea behind HLS is to try to build hardware languages that make use of software abstractions. So there are a number of these tools in existence. Most of them actually are based in C. So there's a tool called LegUp, for example. The idea of high-level synthesis has been around for some time. So for example, Mary Sheeran's early work back in the 80s on UFP. And there's also a substantial amount of work within the functional programming community to build high-level synthesis tools, including Chisel and Rewire. So because I'm mainly motivated by the verification of the Rewire tool, I'll start looking at this. Well, what Rewire does is it takes a subset of Haskell and it compiles it into a synthesizable subset of VHDL. So every Rewire program is a Haskell program, but not vice versa. And one reason that we're interested in functional programming languages is for high assurance, because generally speaking, we have semantics for functional languages and they sort of support formal verification. It's been observed recently that these high-level synthesis tools should be proven correct. And some recent work has shown that some of these tools are, as one might expect, have bugs in them. And there's been a fair amount of work on the on verifying HLS one way or another, or formal methods for HLS. And so for a full accounting of that, please check out the related work section in the paper. With Rewire, it's a freely available system. It has an existing formal semantics. It's been mechanized in Coq. And generally, we're motivated to produce Rewire by high assurance applications. So perhaps you want to create correct hardware devices, or devices that you can prove some security property about, for example. So compiler correctness is most likely familiar to all of you. It's been around for some time. It's one of the older themes in programming languages research. So, for example, here I have quoted a diagram from F.L. Morris's 1973 Popple paper, where he formulates compiler correctness as a commuting diagram. And this commuting diagram formulation pattern reoccurs throughout the literature one way or another. And I expect that you have seen this before. So generally speaking, in these kinds of arguments, one sees that the target language is some kind of abstract assembly language, like the address code or something like that. So the question we ask is, how does this pattern play out within HLS? So where you're producing hardware designs rather than software programs. What kind of semantics would you use for that target language? And how would you relate the formal semantics of a source language like Rewire to a semantics of the target language? Well, if you cast the Rewire compiler into this diagrammatic format, here's what you end up with. We have the Rewire compiler RWC along the top row that produces VHDL. And Rewire has a semantics, or actually has multiple semantics, and so far so good. But VHDL, and Verilog for that matter, do not possess comprehensive formal semantics. Now, this has been a issue that people have attempted to address for some time. So if you'd like more background, Michael Gordon's LIX invited talk is a good source for that. The bottom line is that if you're trying to replay this Morris style diagram for HLS, it's complicated at best by if the target language is a commodity HDL like VHDL or Verilog. Another approach to formulating this problem is simply to create a smaller abstract hardware DSL, something playing kind of the role of 3 address code in a software compiler verification. And so what this hardware DSL should be is somehow small and semantically specifiable. This is where our initial interest in Fertile came about, and I'll say more about what Fertile is in a moment. But the idea is that if we have a hardware DSL like this that we can specify its formal semantics, then we have a chance at replaying or at showing that a Morris style diagram commutes. Notice that even in this setting, the commodity HDL, here VHDL, remains in the overall tool chain of necessity. And the reason for that is that if you want to ultimately synthesize and place a device on, say, an FPGA, then you need to use the vendor's tools. And that means that you need to use commodity HDLs. So we're motivated by the desire to expand the trust zone of high-level synthesis. So I've mentioned this chisel tool briefly, and also Fertile. And this diagram gives some further information. So chisel was designed at Berkeley principally as a implementation language for RISC-V. And within the chisel tool, it produces this Fertile output. And Fertile is kind of a target or hardware independent, low-level hardware language. It's typed and fairly well designed. And so the chisel tool set produces Fertile, and then there's an instruction selection phase that produces Verilog. And from there, you go on to, say, an FPGA board. What Rewire does is it produces VHDL as its output. Now, Rewire itself, it has a formal semantics. Our overall goal is, well, can Fertile or something like Fertile be formalized as a way of supporting hardware verification for HLS generally and Rewire in particular? Another goal we have is that the chisel community has a considerable amount of IP, that is, of libraries that have been written in chisel that produce Fertile. And if we have a Fertile semantics, it at least gives us some chance of formally analyzing those libraries, as well as linking to Rewire, so that in that case we would be able to reuse existing IP and still produce devices in a high assurance setting. So this third-party IP module problem is a recognized problem, in that, generally speaking, third-party IP that one might get to load into, say, a Xilinx Vivado tool. These are vendor proprietary formats that are used, and they're not analyzable. Fertile, on the other hand, is not in a proprietary form. It's open source. So now we go on to the meat of the technical details. So a Mealy machine, as you'll see on the left in the sort of familiar diagrammatic form, is just a kind of state machine. The particular formulation we use is one that when one is in a state and receives an input, here the red, and you receive an input, say on the red, you produce an output and move to the next state. You consume an input, produce an output, and go to the next state, et cetera, et cetera. So that's the probably most familiar formulation of a Mealy machine that you may have seen before. In digital design, however, there's a different formulation, which is more or less equivalent, that you can see here on the right side of the slide. And what this formulation, so this is something that you might find in a digital design textbook, for example. And what this means is, at any particular moment in time, you have an input I, a current contents of local storage, say registers S, and then you have outputs O. So you have a current snapshot of an I, S, and an O. And then at the next click of the clock, the new input is sampled, the current state is sampled. This logic then produces a new output and state. So this is the standard mental model of a Mealy machine, and we're interested in formalizing that. Well, we've formalized that in AGDA as a co-inductive record in this way. So our formalization says, well, a Mealy that is parameterized over inputs, states, and outputs, what that really is a function that says, if you give me an input, I will give it, and a current state, I will produce the next output and register state. I have a current snapshot characterized by now. And then there's a next, which says, if you give me another input, I will produce the next Mealy machine. So this is our formalization of Mealy machines. There is a basic constructor for constructing Mealys, which we call unfold M. And what unfold M does is it says, look, if you give me this state function that captures the output and next state logic, and you tell me where I am, I will construct the appropriate Mealy. That's all that means. Mealy machines also have a stream semantics. So what this means is we call this transcript. If you give me a Mealy machine and you give me an infinite stream of all inputs, I will give you the stream of snapshots that arise from that the stream of inputs. And so just as a simple example here, of course, is Fibonacci. I would have to turn in my union card as a functional programming nerd if I didn't include Fibonacci here. So this is a 4-bit Fibonacci Mealy machine that basically just, well, calculates Fibonacci. The details are in the paper. So in terms of unfold M, we can define a number of useful operators on Mealy machines. So for example, there's a parallel operator. You give me M1 and M2, then M1 parallel M2 is a new Mealy machine that now operates M1 and M2 in parallel. Or there's a connection operator which we call feedback, which says, basically, you give me a Mealy machine M and functions that characterize its output and how the inputs and outputs are connected, and I will give you this new machine. And for example, if you want to pipeline a machine, so you want to take M1 and feed its output into M2, then the pipeline operator, pipeline M1, M2, will create that single Mealy machine. Now, what the device calculus is simply a syntax for Mealy machines. So I don't provide all the details here, but it's basically where I've written SNP is basically a lambda calculus syntax. It's in De Bruijn format. It's in this implicitly typed syntax style that is common in AGDA. And so we introduce just by comparison, syntax for unfold, parallel, and feedback. And there are also syntax for bit operations and variables and apply and lambdas and all that sort of thing. Details are in the paper and they're not surprising. We can then introduce a device calculus semantics. It's in this, what they call, it's in this dependently typed style where if you give me a typed term and an appropriate environment, I will give you a thing of the appropriate type. So the function value and exactly what an env is and all these things are not necessarily surprising if you're familiar with dependently typed functional languages like AGDA, but the details are in the paper, and but really the bottom line here is that the syntax of the device calculus is mapped to the appropriate constructions in the Mealy world. So that is simply what the device calculus is. And now I'm going to present the case study that for Fertile. Now, what we do in the paper is we capture what we call idealized fertile. So it's really inspired by fertile. We're not claiming here to have the gold standard semantics of fertile, but we do cover a lot of the constructions of fertile, a representative sampling of fertile. Fertile, incidentally, stands for flexible intermediate representation, for RTL. And over here, we can see the just as an example, a simple fertile module. And so if you look at the components of this module, there are here in red, there are inputs, there are registers, so these are the state things, there are outputs, and there's also, those are fairly self-explanatory, more or less. And here in the lime green, you can see what are called connections. And what connections are, they're really connecting the input and registers to the outputs and registers. So in effect, a connection is really a kind of lambda, really, of this type. And so our formal analysis of idealized fertile makes that precise. Fertile circuits have this simple block structure. Now, this sequence of lets, these are simple lets, not recursive lets, and fertile itself does not contain lets, or does not make this block structure explicit, but we do an idealized fertile. It's useful. For the idealized fertile semantics, or IF semantics, we provide a type system. So this module furfib is mapped to this module type, where you have a module, its inputs are bit cross bit, its registers are W4 cross W4, those 4-bit words, and its outputs are 4-bit words. And the type system, you can show that furfib has this specific type delta. Then the way we semantically model idealized fertile is as we translate it first into device calculus and then use the device calculus semantics. So we have this function TRC for translating circuits into devices. Note that a translated idealized fertile mod or circuit becomes a device. And in general, any idealized fertile module is mapped to a device in device calculus. And then our semantics, as I mentioned, is via translation. So we translate the idealized fertile program, and then we use the device calculus semantics to create the particular Mealy machine that we can then reason about if we want to. And just as a sanity check, fib4 prime, that is the meaning, or fib4 prime, that is the meaning of furfib4, produces the same output as fib4, which we saw earlier in the presentation. Fertile modules also have instances. So these are our like submodules that refer to previously defined modules. And the way these are modeled in the device calculus is using the feedback and parallel operators and the various output and connection functions are derived from the connections part of the module. This would be a simplified form of fertile, maybe a next generation fertile, would perhaps replace instances with parallel operators and a connection operator like feedback. So conformance, how do we compare fertile, which is has no formal specification for direct comparison with idealized fertile. There are only informal definitions of fertile at the project website, and there are several publications as well. Well, the way we test conformance is we grabbed some unit tests from the fertile code repository, as well as a simulator they wrote for fertile, and we compared the outputs produced by the fertile simulator against the AGDA semantics that we've outlined here. And for all of our unit tests, mind you, this was not extensive testing. We're talking about 5 or 6 tests, but we ended up with identical output. And we also created a formal equivalence statement between the AGDA semantics and a putative small step operational semantics. So a hardware designer is more likely to understand a small step operational semantics than our AGDA semantics. That might be the case. In any event, another difference, or a difference between idealized fertile and fertile, is that idealized fertile assumes precisely 1 clock. That was a simplifying assumption. Fertile has fine-grained multiple clocks. Now, this was not a problem when we were doing the experimental evaluation, but this was not a problem when we were doing the experimental evaluation, because most of the unit tests are uniclock for fertile. What this fine-grained multiple clock, what I mean by that is that if you have 2 registers B and C, they can be on distinct clocks. And so a connection statement like this can have a difficult to determine meaning when the clocks are fine-grained. An alternative to fine-grained, that is where each register is attached to a clock, are what we might call multiple clock domains. These are where individual devices are attached to a clock. And this is something we will explore in future work. So in summary, what we've presented here is the device calculus and its mechanized semantics, as well as a case study that mechanizes a substantial subset of a fertile-like language. Again, we're not saying that this is the gold standard for fertile, but we believe it's a starting point for it. In future work, we outline 2 particular goals. One is to explore multiple clock domains as effect types. So here we might say have a clock sublanguage that are effects, like effect labels, and we attach an effect label to each device, and then have a new kind of parallelism, sort of an asynchronous parallelism that creates a device that has this kind of join of the clocks. So multiple clock domains are a recent extension of the leg up high-level synthesis tool, and future work considers formalization of something like that within Rewire. And so that is our one future work theme. Another is to explore a verification of the Rewire compiler. At 2.6, we've produced a number of denotational semantics for Rewire that have been mechanized in Agda, Coq, and Isabelle. These are kind of inspired by this device calculus and its semantics. So a Rewire device, the domain associated with it would be something of this form, that is a stream-based semantics that says you give me an initial snapshot, the stream of all inputs, and I will give you the stream of all snapshots. For Mealy machines, the semantics is something quite similar. So a mealy has that initial snapshot encoded within it. And then a compiler from a rewire calculus formalized in AGDA, so that's what this this kind of lambda might be, will be compiled into a appropriate Mealy machine typed thing in the device calculus. So implementing this compiler is not, or has not been done, but this is the future work. Then the correctness of this kind of formulation of the compiler would be along these lines, where this is just basically the Morris diagram, written out in non-diagrammatic style. I want to thank you for listening to my talk and express my regret that I could not be there with you.